first let me thank the Academy for inviting me to give this talk. I wouldn't be standing here without the generous support of DST and DAE who have supported my research for many years, and my friends in the Department of Physics. And this particular talk, my primary collaborator is this young gentleman here. His name is Nanda Gopal. He was an undergraduate student here, and he's now at Caltech, and Roderick Mosner, who is at Dresden. Okay, so what I'm going to do is, I'm going to tell people from other fields why condensed matter physics is the coolest thing to do. So I'll introduce some of the ideas of condensed matter physics, and I'll tell you a little bit about the notion of phases, which Professor Banerjee just mentioned. And I'll tell you a little bit about some of the new phases that have come up. So these are what are called as topologically ordered phases, and then I'll tell you a little bit about the youngest additions to this category, and these are called the Fracton order phases. And then I'll give you little snippets of 3 pieces of work that we have done. And I have to apologize to the experts like Bhaskaran, etc. here that this is a talk meant for a broad audience, so it will be very general and not very technical, at least the beginning part of it. Okay, so let me give you a snapshot of where condensed matter physics is at and what we do actually. So what is the main question in condensed matter physics? So you see, you start with a set of things. So those things could be electrons, atoms, molecules, human beings, stars, quarks, anything, right? And then we ask, when you mix them together or put them together, what all stuff you get? So if these things are atoms or molecules, and if the question being asked is a 3-mark question, then the answer is solid, liquid, and gas, right? So solid can be like crystals that we consume, liquid is some water kind of thing, and this is the fresh air that we breathe. So any of these things are examples of phases. So you can ask a question, what do you mean by a phase? So one can give a very nice technical answer for this in terms of renormalization group, etc. But a very simple way to understand it is that a phase is something that exhibits a certain characteristic set of properties. So for example, all solids we know, at least for small enough perturbations, resist shape and size changes. So that's actually characteristic of being a solid. Okay, so I'm going to now tell you a little bit about quantum condensed matter physics. So what is the story here? So here, the things that we are interested in are intrinsically quantum. So some things are very light, like for example electrons. And when you put electrons together, you can get different phases of electrons. Okay, and if you do a course in condensed matter physics, and you're not stopped by the pandemic and so on, you will find that the course will cover roughly 5 phases. The first is the metallic phase, and this is like the liquid phase that we know. So the metal is actually just like a liquid of electrons, a fluid of electrons. That is, when you apply an electric field, it flows just like when you apply pressure in a pipe, water flows, right? I mean, this is quite similar to that. And then you have a magnet. Then you have an insulator, like a diamond is an insulator. It doesn't conduct electricity. And then you have some more exotic things called the superconductor, and you have something called the quantum Hall effect, or what are called as Phil-Landau levels. So these are the sort of phases that we teach students. And the natural question to ask is, why should you bother about all this, right? So if you think about this for a minute, you realize that it's the electronic phases that run the world, right? So think about anything that I'm holding, right? Mobile phone, anything. So it's made of basically 3 phases of electrons. So we are using the properties of 3 phases of electrons, and that's it, right? We're using magnets, insulators, and metals. Nothing much more in this, right? So just these 3 phases give us all the technology that we see around us. Okay. So now it's very natural to ask a question: are there more phases? And you can see that if there are indeed more phases, then there are many more possibilities that are going to open up. Okay. So that's the question really, right? So are there more phases with exotic properties? Right? And can it lead to new technologies? So that's from the pitch to the funding agencies. So what's the pitch to the theorists? Is there a systematic classification of phases? So this is not unlike what happens in mathematics. So for example, you can ask, how do you classify manifolds? How do you classify algebras? How do you classify groups? So it turns out that there are very deep connections to these questions and those questions, right? And I'll show you some of those connections. Okay. So are there other phases? And the answer is an overwhelming yes, right? And what is this motivated by? And it's motivated by quantum computers. So all of you, I'm sure, have not escaped the the news of quantum computation and so on. So if you look at any of these computers, like the ones that we are using to project here, you see all of information is stored in zeros and ones, and you have ways to manipulate these zeros and ones, move them up and down and so on, and then you can churn out information, extract numbers out and so on. The idea of quantum computation is that I use two quantum states to denote 0 and 1, and I can put information not just as 0 and 1, but in some sense some linear combination of these. So if you want to think of this, I can think of the information space, instead of just being north and south pole, as being any point on the surface of this. So it's called the block sphere. And I don't have time to discuss this, but once you set this up, then it turns out that this allows you to solve a certain class of problems which are not accessible to classical computers very efficiently. Okay, so that's the promise. And again, I don't have time to point this out. So if this is done, and if all of us can carry a quantum computer in our pocket just like our mobile phones, then we'll be living in a completely different epoch of human evolution, right? And the reason for that is just mind-blowing. I mean, this security, lots of things will change, and hopefully, I hope that I'll live to see that day, right? And it will be like epoch-changing, like these things like electricity, vaccines, etc. So what's the problem here? Why don't we have a quantum computer at ambient conditions? So it turns out that these qubits, as they are called, they're very sensitive to all sorts of things. So if you put information there, imagine that it's on the surface of a sphere, it'll sort of slowly wobble around and it'll sort of move around, and you'll actually lose all the information, right? So it's very, very hard to control this qubit, and you can initialize the qubit to the point that you want, but it won't stay there, because there are things that your neighbor may have a cell phone call and that will kind of disturb your qubit. So the question now is, how do I create a qubit which is what in the community is called coherent, which will keep the information for a long time? And this is kind of one of the key problems in quantum computation. So now what I'm going to do is, I'm going to take these bad qubits and I'm going to construct phases of qubits. So I'm going to put a bunch of qubits together, and I'm going to create a phase of those qubits whose ground state is the lowest energy state, will become a new qubit for me. Okay? So I'm going to talk about phases of qubits. So what's that? So, okay, this is a slightly technical term here, but it's very simple to understand. I call this Z2 gauge theory. What is this? This is simply electromagnetism, as you know it, right? Electric charges moving around, etc., but in a discrete setting. So the fields are just 0 or 1, right? That's what this is. So if you construct this, so what are these red dots here? These red dots are these bad qubits. So you put a bunch of bad qubits and you sort of make them feel some kind of, or make them generate some kind of electric and magnetic fields. Then it turns out that this system has a fantastic property. You take some array of qubits like this, you'll find that their ground state, if you arrange them so that they're covering a torus, the ground state will be 4-fold degenerate. That means there are 4 states which are exactly equal in energy. And it turns out that you cannot split this degeneracy so easily. They're protected by topology, right? And topology and entanglement, I should say, right? So this is what happens. So these are what are called topologically ordered states. Okay. So how do we describe them? So we can describe these things from the physics perspective by what are called as topological quantum field theories. In this particular case, you can give an abelian Chern-Simons theory. And this toric code, as I pointed out, can be a starting point of a quantum memory, in the sense that I can use, say, I can arrange of these 4, I can pick 2 states and make them as the north and south poles of my block sphere. And that's where I store, then I can linearly combine them, and that's where I store the information, and the information is topologically protected, right? So that's the idea. So are we successful in this? By the way, this toric code has been realized experimentally. I should put a slide, I'm sorry, I just came to my mind when I was working here. Anyway, so it turns out that this is not such a good idea when you go to finite temperatures, because such electrodynamics that I described, it will simply pop out charges out of the vacuum, actually magnetic charges out of the vacuum. And these things, just like electric charges can move around freely, they will move around freely and this will gain entropy for you. Disorder will increase and it will sort of melt this toric code order. This topological order will instantly melt at finite temperatures. So in a sense, this kind of approaches to trying to develop a quantum memory is kind of not a good idea because it has this problem. So how do you try to solve this? And that's where these new phases come in. So they are called Fracton phases. So how do we start the discussion of Fracton phases? So what you do, you define a new kind of electromagnetism. So what you do is you say that there is some three-dimensional cubic lattice on which, again, I'm going to, at the corners of each cube, I'm going to put, at the edges of each cube, I'm going to put a bad qubit, right? And then I'm going to say that the magnetic field is something more complicated. It's a product of these 12 spins. So in some sense, it's higher gradients are involved here, right? And then you will see that such a model, this is called the X cube model, has some fantastic properties. So you will find that this has sub-extensive ground state degeneracy. That means if I have a system whose size is nx, ny, nz in 3 different directions, it will have degeneracies which are some 2 power sum of that number, right? This is called sub-extensive degeneracy. And then, so why would you call them fractons? So it turns out that if you try to think of excitations of this, I pointed out that you can excite magnetic charges out of the vacuum. You can do that in the X cube model also. But what you will find is if you excite one of these and try to move them, they cannot move, they are locked in. They cannot move not because of some energetic constraints, but because the theory simply doesn't allow them to move in the same energy manifold. If you try to move, you will create more and more of these, right? So this is why they are called fractons. So how do you describe them? So that's what I'm going to discuss first. So it turns out that there are ways to describe these kind of things with higher rank gauge theories. So let me just give you a very quick idea of higher rank gauge theories. So suppose I had some world in which the electric field was a second rank symmetric tensor and my Gauss law was 2 divergences of this electric field is the charge density. Then you will find that charges are conserved and the dipole moment is also conserved, which means that an individual charge cannot move because if an individual charge moves, it will change the dipole moment. Okay? So then the question is, can we write a theory which generalizes this to arbitrary dimensions? The charges can be point-like, they can be line-like, surface-like, and it can be an arbitrary dimension. You can have conditions on all multipoles, certain multipoles of the charges. So you can write a theory for this, and this is what we did. So I'll just very quickly flash this. This is just to show you that I can actually write LaTeX very complicated equations. You're not supposed to take anything more than that out of this, right? Okay. So what is the main mathematical thing that we need, crutch that we need here, is that we need the notion of what are called as K-n tensors. So these are actually symmetric tensors of anti-symmetric tensors. That's the very simplest way I can put it. So so these are the objects, and the gauge fields will have a certain K-n structure, and from there you can actually define what are the electric and magnetic fields, and you can define a gauge transformation. You can write down a Lagrangian for which everything is invariant, and the gauge invariance will now force a certain continuity equation, which is what I'm showing you here, which will force that these charges which are of certain type, so for example these are k-1 dimensional extended charges, they will have dipole or multipole constraints up to 2n pole constraint. So in some sense what we are after here is we are after trying to write down phenomenologically what are the sort of theories that can give you fractonic excitations and so on. So that's the example of this. So this is the general framework. Now I'm going to show you how to apply this general framework in day-to-day life, and maybe a couple of examples I will show you. Okay. So now if any of you have a sheet of paper and just draw not a straight line but some arbitrary smooth curve and try to fold the paper along that smooth curve which is curved, you will find that it's not possible to do so. You will find that it will produce extra folds and so on. So you can fold a piece of paper only along a straight line. Okay, and I'll show you that's the simplest example I know of day-to-day life, which is phenomena of fractonicity. Okay. Okay, so how do I think about paper? So this is the common observation that I told you about. So paper can be thought of as what in the standard textbook would be called as a thin plate, right? And if you think about what you need to describe that plate, it's just the displacement, the mid-plane displacement of the plate. Okay. Okay. So that's what, so this is, and the strain is actually characterized by something called as curvature, which is two derivatives of this. And what I'm going to do is, I'm going to think of defects in this plate. So you see, you can have a fold defect, you can have a tear defect, right? So this is, you can write down a theory for this. I'm going to now introduce a different kind of gauge theory, and the gauge theory has a vector potential, a scalar potential, what we would conventionally call a scalar potential in Griffith's, the elementary textbook on electrodynamics. That is a vector, and the vector potential is a second rank symmetric tensor. And then what you will find is that you can write down a very nice Maxwell-like theory with these kind of gauge transformations. So what are the charges of this theory? You will find that the charges of these theories are vectors. And you will find a continuity equation where these charges are conserved. But in addition to that, the moment of the charge is also conserved. Not the dipole moment, the moment of the charge is conserved. This is in 2 + 1 dimensions. Okay. So what happens here is that if I have a point charge pointing in a certain direction, to preserve this moment, the point charge can move only along its direction. Because it's a vector charge, so it's like something with a vector, it can move only along its direction. Okay. So here's the thing that we showed. So we showed that this defected plate theory is actually dual to, in a very field theoretic sense, to this vector charge gauge theory, right? So you will see that this is the duality picture, and how do we then understand the folding phenomena? Okay, so you see, if I take a fold defect from the perspective of the plate, what is there here is that there is a jump in the slope of the plate. There is a jump in the slope of the plate. When I look at it from the gauge theory perspective, this point where the jump in the slope ends, that is the source of that's a charge, that's a vector charge of that gauge theory. And what does the theory tell us? The theory tells us that this charge can move only along its direction. That's exactly saying that the fold can move only along only along a straight line, right? So we get a perspective of why folding takes place here only along straight line because of this. That's because the dual gauge theory is a fractonic condition, and this. So it's some global thing of keeping the continuity of the paper at straight in the dual language is captured by this the fractonicity constraint. Okay, so that's that. So we can also understand tearing. I'm not going to tell you about that. So finally, we decided to try to see how to realize some of these things in. By the way, all that I told you there was classical. I'm going back to quantum. So how do we realize these things in some real system? So one of the ways to think about this is, so we are sort of taught that we try to take everything from some UV degrees of freedom and try to construct some quantum field theory. So typically quantum field theories are described by, you take some fields, attach them to points on a manifold. But what we are going to try and do now is, I'm going to go beyond the manifolds. I'm going to create arenas which are not manifold-like. So how can I get this? So you see, now there are many ways to put up qubits together and construct all sorts of different things. So it is possible to go beyond manifolds. Yeah, so I'll just show you that we have constructed theories on such arenas. These are based on trees, hence arboreal. And you will see that we can define various kinds of theories on this. And the punchline here is that even the simplest gauge theory, with simple gauge theory is fractonic, and we have worked out various things on this. And let me just tell you the final punchline. So the big questions in condensed matter today are the following. We have understood that we need two important concepts to go beyond what we knew before. One is topology and the other is entanglement, right? And using these ideas, people have completely classified what are the phases of non-interacting electrons. And you can see that if the mathematicians will see that these are the Cartan labels of symmetric spaces and so on. So you see that there's some reason fermions have to be there because symmetric spaces had to be realized by someone, and those are fermions. And some of the open questions are, what is the general framework for classification, and where do fractons fit in, and how do we go beyond manifolds? Okay, and I'll tell you my punchline is this. That these are the phases of matter of many particles that control evolution so far. I think these new phases is what is going to take us to future. So sorry for extending a little bit.
Quantum models,
yeah.
And then fractons, and then you came to papers and origami. So is there any quantum origami you are implying?
It's possible. I mean, I haven't tried to quantize that theory.
It will be attractive to young people. young students and so on, quantum origami.
No. The juxtaposition of the two words is very interesting, no doubt. But yeah, we have not tried to quantize the theory yet. Yeah, it's possible. Yeah.
It's a very quick question.
Yeah.
That you are talking of Gates theories, but these are non-relativistic, right?
No, some of them are relativistic, some of them are not relativistic.
I see. Because I was.
It depends. So we can construct a class of fractonic theories. So we have something called the dynamical exponent, Z. So with Z is equal to 1, there will be some emergent Lorentz. But
Okay.
yeah.
No, my question really was whether
Yeah.
I can translate it to a relativistic domain.
Of course you can. There are examples of those.
Okay, thanks.